Well, let's go ahead and get on to our next lesson. The lesson is, what is nuclear energy? I want you to think about these bell assignment questions as we progress through this video. I want you also to stop the video and draw atomic models of nitrogen, radium, radon, and francium, and show the correct number of protons, neutrons, and electrons. Bring that to class tomorrow. And then I want you to look at the symbol below. What is it and what does it mean? I want you to think about that before we actually begin. Do you think good things? Do you think bad things? Hopefully throughout this video, this next unit, you're going to learn some really important applicable things in your life. Nuclear chemistry. When you look at the word nuclear chemistry, what do you think the word nuclear is referring to? It's referring to the nucleus, absolutely. So these are the things that we are going to cover in this next lesson. You're going to be able to describe radioactivity, compare and contrast stable and unstable atoms, and then finally identify the sources of radioactivity, and that'll probably come in a couple, the next lesson. What is radioactivity? And if you're following along with the fill-in notes, I want you to go ahead and use the fill-in notes and fill them as we go. Radioactivity is just simply the process when an unstable nuclei, an atomic nucleus, gives off particles or releases energy. And I want you to think about this. Okay, what do we have in the nucleus? We've got all these protons, and what kind of charge do they have? Positive and positive. Well, what does a positive and positive nucleus, what did the positive and positive charges want to do? They want to repel each other. So if we think about it that way, why is it that the nucleus stays together? And then what are we saying when we've got, sometimes they don't stay together. They actually start to fall apart. So let's take a look at that question. Why are they unstable? So if you go back to that nucleus where you've got positive charges, there's something that actually holds them together. It's called the strong nuclear force. It's the force inside the nucleus holding it together to overcome those repulsive charges. I've got a little video called Nuclear Stability. I want you to go ahead and watch this little video, and we're going to talk about it a little bit more in depth.
An atom is held together by the attraction between the positively charged protons in the nucleus and the negatively charged electrons. But particles with the same electrical charges repel each other. Why doesn't the nucleus fly apart? The reason it holds together is because of the strong nuclear force, one of the fundamental forces in the universe. This force operates between the protons and neutrons at extremely short distances. Elements with atomic numbers from 1 to 20 often have the same number of neutrons and protons. But elements beyond 20 need increasing numbers of neutrons to hold the protons.
So we will get to the rest of that in the next lesson, but I wanted you to concentrate on the strong nuclear force and to think about why that nucleus is stable or unstable. And so all nuclei with more than 83 protons in the nucleus are automatically radioactive. And so let's take a quick little comparison here. If we've got the number of protons equal to the number of neutrons, we can usually say that that atom is very, very stable. if the number of protons are not equal to the number of neutrons, then most of the time we are going to get some kind of an unstable atom that we consider to be radioactive, and it's going to go ahead and go through the process of decay. And so a radioactive isotope is just simply something that has a different number of neutrons. Remember, we've talked about isotopes in this particular unit, or this year. Practice writing in isotope notation. Now, this is a new form of isotope notation I need to make sure you understand when we are talking about nuclear chemistry. And the first thing I want you to see is the example radium. I'm going to draw that in isotope notation. So if you look at the periodic table, you find the element radium. Its chemical symbol is Ra. Then you find the atomic mass that is on the periodic table. That is 226. And we find that the atomic number, or the number of protons, is 88. So I want you to think to yourself, is this element stable? Well, look at how many protons there are, 88. It is not stable. Its nucleus will not be able to hold together. How about carbon? If we look at the example in the periodic table for carbon 14, and we look at the periodic table, ooh, this is a little different than the one that's on the periodic table. It's got a different mass. It's got 14, which is fine. Elements can have a different mass, and we know that those are just simply isotopes because of the number of neutrons has changed. And then if we go to carbon, we know that the number of protons is 6, and the number of protons and neutrons does not match. We've got 8 neutrons in this example, so therefore carbon 14 is going to be unstable. And the last example that I want you to do is boron. So we'll go ahead and do this one together. So we've got the chemical symbol B, and we know that boron is element number 5, which means that there are 5 protons, and its atomic mass is 11. And so this format right here is the format you're going to be needing when we are talking about nuclear chemistry. Now, one other important thing that I want to remind you, we are now in a unit of nuclear chemistry. You must understand that the chemistry we are talking about now is a completely separate branch of chemistry compared to regular chemistry. All the other chemistry we've talked about up until this point has to deal with the electrons. And if the electrons are stable, that outermost shell, now we are changing our focus to the nucleus.